Section 21.4, the mass spectrometer. This is a really cool setup for how you can determine the mass of any given atom or molecule. So let's walk through the setup. First, we have this ion source, which is where you put in the substance you want to study. It's vaporized and it's made into an ion. So it's ionized, that has an extra, one of the electrons is kicked out, so it has of plus E, 1.6 times 10 to the negative 19 C. Now that it's charged, if it's held between this potential difference V, it's going to accelerate. It starts out at rest. By the time it reaches the end of the potential difference, it's now moving faster. You can figure out how fast it's moving if we go back to the method of saying the kinetic energy equal to the electric potential energy. Electric potential energy is the charge plus E times the potential difference V. It's equal to 1/2 mv squared. So you can use this to solve for how fast it's moving at the end, right? And you find that that speed is given by 2 times E times the potential difference V divided by the m, and with the square root taken. Now that with some speed, it gets sent into a region with a magnetic field, where the magnetic field is here shown out of the paper. So what's the direction of the force it experiences? Well, we can use our right-hand rule, right? The velocity is up, magnetic field is coming out of the paper, so at us. So the force is to the right. That's going to cause the path to bend, and it creates this circular path that the ion would follow at a set radius. Now, at certain radiuses, that will curve around and come into a detector. What determines that radius? Well, the radius is set by the mass, the speed that's moving at, divided by the charge, and the strength of the magnetic field. Here we have the magnitude of an electron charge because we lost an electron, so it's just positive. And so this sets how large the radius will be. Now, if we eliminate velocity by taking our equation for V and plugging it into this, and then rearranging to solve for mass, we would ultimately arrive at this equation after some algebra. That the mass is equal to, in parentheses, the charge of an electron times the radius squared divided by 2 divided by the potential difference and times the magnetic field squared. What can be done then is we can keep what's in parentheses constant. We can keep it ionized in the same way. We'll keep our detector at that one radius that we're interested in and keep the potential difference the same as well. But we'll adjust the magnetic field. What does that mean? Well, if we adjust the magnetic field, like if we increase it, it's going to correspond to an increase in mass as well. And we'll be able to detect higher masses with a stronger magnetic field. And that's what scientists do in order to determine the mass of various substances, even in surgery, to determine the presence of gases in a patient's lungs, like anesthesia. They can use a mass spectrometer. And so the output of this looks something like the following. This is the mass spectrum of naturally occurring neon, and it shows 3 isotopes. So on the x-axis here is B squared, which is proportional to the atomic mass by the equation we just saw. So the strength of the field is squared. And then the output from the detector tells you the relative abundance. So you don't see much, and then all of a sudden the detector's like, boo, 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 boo. It's detecting a lot at what is known as neon 20. And then it goes back down to not really detecting anything. And then it's able to detect smaller blips for neon 21 and 22. Turns out neon 20 is the most abundant in naturally occurring neon gas. But you can look at those different ratios and understand what is in your substance of interest using physics. Pretty cool.